All right. So where we left off, we had been looking at a Hess's law problem, and I had mentioned I loved Hess's law problems. I thought they're kind of fun. They're like little analytical problems to solve. And when I ask questions about Hess's law on the test, sometimes the performance isn't quite as good. I suspect though that a lot of students do is they kind of just look at it, try to do it in their head, add the numbers together, and then bam, there's their answer. And if their answer doesn't match mine and I can't see what they did, then they don't get any credit. And so it's a relatively big point weighted problem just because, there's a lot of steps involved. So I have a feeling, I suspect that that's what it is. So what I've started to do is just really emphasize showing your work in this format. That's going to be tricky. Like you're not going to want to type in 5 equations. So what I'm going to ask you to do on the quiz and on the test, and you'll see this with the practice quizzes, is I might say, okay, when you look at your 2 given equations, and this is your target equation, what do you have to do to equation 1 to make this work? I'm not asking you about all of it. We're just going to look at equation 1. What do I need to do to equation 1? Well, if I look, right, the carbon monoxide is in equation 1, right? And it's in the target equation, but it's on the other side, right? Instead of being a reactant, it's now a product. So multiple choice, do you need to flip it? Do you need to multiply? Do you flip and multiply, right? So in this case, we already know we're going to have to flip equation 1. Then what I also see is instead of a coefficient of 1, I need a coefficient of 2. So I'm also going to multiply. So for equation 1, my answer would be, okay, I need to flip it and multiply. For equation 2, methane is on the correct side. It's a reactant, but I also need to change the coefficient. In my given equation, there's no coefficient. In my target, I need a 2. So I'm going to have to multiply equation 2. So what I've done on the quiz and the test, and again, only to make this easier to test, because showing your work here, typing all that in, I think might be a nightmare, is that I'm just going to say, okay, equation 1, what do you need to do to it? Okay, well, I need to flip it and multiply by 2. Okay, equation 2, what do you need to do? Just need to multiply by 2. All right, so let's try another example of Hess's law and kind of go through the same process. So in this one, we've got ethene combining with hydrogen to make ethane. All right, nomenclature coming when you get to organic, so don't worry about the name so far. So I've got these target equations, the target equation, I've got the given equations here. So I'm just going to label it easier for tracking. This is equation 1, equation 2, equation 3. And then the one that we're looking for, right, is our target. So question is, what am I going to do to each of these equations? And it's you might look at this and be like, well, I've got 3 equations given to me, but I only have like 3 substances here. So like, how is all this going to work? There's a lot of stuff here I don't need: oxygen, CO2. So this one, it might look like it's worse, but it's really the same idea. First thing I always do is I pick one of the substances from my target equation. So like I'm going to highlight the ethene, the C2H4 on the reactant side. And I go and I look for it, right? It's not in equation 3. It's not in equation 2. It's right here in equation 1. Okay, so the ethene is going to come from equation 1. So again, if this were that multiple choice format for the quiz, I would say, all right, what do we need to do to that equation 1 in order to get this working for us to get to the target equation, right? Step by step. So the ethene that's in equation 1 is a reactant. In my target equation, I need it to be a reactant. Good. So I'm not going to flip it. Then I look at that's the only 2 things you can look at. Do you need to flip it? And do you need a coefficient in front? So we don't need to flip it. Coefficient, right? Implied 1, coefficient implied 1. So we don't need to do anything to equation 1. So I'm just going to write a little note. Equation 1, we are going to leave it as is, right? And then that means that delta H value won't change. So the delta H of negative 1410.9 is also just going to be an as is. All right, now let me go and look at a second substance. All right, let's look at the ethane, the C2H6 on the product side. So the C2H6 on the product side, that is not anywhere in equation 3, but I do see it in equation 2. So the ethane right here, right, that's going to come from equation 2. So what do it seems weird to say, don't worry about any of the rest of it, but that's actually true. Don't worry about any of the rest of it. Just focus on that substance, the ethane. Number 1, is it on the correct side of the arrow? No, I need it on the product side. In my given equation, it's on the reactant side. So I already know for equation 2, I'm going to have to flip it. Then the next question is, does it have the correct coefficient in front? And again, the answer is no, because in my given equation, it's got a 2 in front, but in my target equation, I only want 1. So you're always thinking the equations that are given with the delta H, you're always asking, what do I do to these to make them get to my unknown? Because that's really what we're looking to do here for this reaction that we're given without the enthalpy. That's what we want to figure out. We want to know the delta H of this. So your question is always, of these given equations where I have the known delta H value, what do I do to these equations, each one, right, to make it work for me to get to the target? So you look for those discrete substances, right? The ethane in my target equation is only here in equation 2. So what do I need to do? Well, I need to flip it. We talked about that. I need it on the product side. It's on the reactant side. And then the other thing is I only need 1 ethane. And in my given equation, it's got a 2 in front. So I'm also going to have to multiply. In this case, it's going to be by 1/2. I need to cut it by 1/2. So what I'm going to do with that delta H is I'm going to change the sign, right? Because we flipped the equation. If it's exothermic one way, it's endothermic the other way. So it's now going to be 3,000 positive 119.4. And then we'd multiply it by 1/2 because that's what we're going to do to the chemical equation. So whatever you do to the equation, you do to the delta H. If I'm flipping it, I'm going to change the sign, negative to positive. I flip the sign. If I'm multiplying through by 1/2, I'm going to do the same thing to the delta H value. All right, then the last substance is the hydrogen. In the target equation, that's what we're going to go look for. I see hydrogen gas coming right here from equation 3. Hydrogen by itself, H2, nowhere else in those first 2 equations. It's just coming right here for equation 3. So if I look at my hydrogen in equation 3, so I'm going to write a little note. This is coming from equation 3. 2 questions. Is it on the correct side? Yes. Reactant, reactant. Okay. Then the second question is, what about the coefficient? Well, I've got a 2 and I need it to only be a 1. So I'm going to multiply that by 1/2. So if the question on the quiz is like, okay, so what would you do to equation 3? You would say, I just need to multiply. Equation 2, you're going to have to flip and multiply. Equation 1, you would just leave as is. So that's what the quiz questions are going to look like. So if I'm multiplying my equation through by 1/2, then I'm going to multiply that delta H by 1/2. All right. And so now what I'm going to do is rewrite my 3 equations and make sure that they're going to end up at the target equation that I'm looking for. So my first equation, we're going to just rewrite it as is. So C2H4 plus 3 O2s to make 2 CO2s and 2 H2O. Delta H doesn't change. It's just going to stay negative 1410.9. Right now, my equation 2. All right, I always keep the arrow in the same place. It makes it easier when you go to cancel things out because you'll see it. I think it's easier to see. So we decided with equation 2 that we were going to flip it, all right, which means reactants come products, products become reactants, and divide it by 2. So on the product side, instead of 4 CO2s, they're going to go to the reactant side, but half of that means it's going to go down to a 2. So I've got 2 CO2s. And then instead of 6 waters, it's going to become 3. All right, so I took my 2 products, turned them into reactants, and I divided them by 2. So I've got, instead of 4, I've got 2 CO2s, and instead of 6, I got 3 H2Os. Now on the product side, the ethane now becomes a product. Instead of 2, there would be 1, so C2H6. And then instead of 7 oxygens, I would have 7 over 2. All right, so I've got 7 halves oxygen. So what happens to my delta H? Well, like we talked about, instead of it being a negative like it was up here, it's now going to be positive. And then because I cut the equation in half, I need to cut my delta H in half. And so what I get here is positive 1,559.7. All right, the third equation, we have the only adjustment we're going to do is multiply it through by 1/2. So instead of 2 hydrogens, I'm going to have just 1. instead of 1 oxygen, I'm going to have 1/2 oxygen. Okay, this is going to drive me bonkers today. Okay. And then on the product side, instead of 2 waters, we're going to have just 1. And so the delta H there, we're just going to take that negative 571.6 and divide it by 2. So it's going to stay negative because we didn't flip it. We just got to cut it in half. So on this also keep track of the positives and negatives, right? Because it's important when you add it all up in the end. All right. Then if I add everything up together, okay, so we're going to add all of that together. When I go to add, this is why I line it up here with the arrow. To me, it seems easier to follow. Now the C2H4, that needs to stay in place, right? Because that's in my target equation. So hopefully that's not going to cancel out with anything. And obviously it doesn't. Then if I look at water, all right, so I've got 3 H2Os on the reactant side. And on the product side, I've got 1 and 2. So there's 2 plus 1, 3 waters to cancel out with the 3 waters, right? So your arrow is like, okay, we're trying to get rid of like things on both sides of the equal side. Your arrow's like your equal side. So these are all of my products on the right. These are all of my reactants on the left. So if I bring into this 3 waters, and at the end, I have 3 waters, that means water didn't play a part in this reaction. That's good because it's not in my target equation. So any like terms on both sides of the arrow cancel out. So 3 waters and 3 waters. If I look at CO2, I've got 2 on the reactant side. I've got 2 on the product side. So those are going to cancel out. All right. Now, if this had only 1 CO2 on the product side and there were still 2 on the reactant side, you haven't canceled them out. Then you'd still have a CO2 here. All right, but we don't have that problem. Then the other thing we've got is 7 halves, which is 3.5 oxygens on the product side. There's my 3.5 oxygens on the reactant side. So I've got 3 in the first equation, another half in the third equation. So those go away, and that cancels with the 3.5 on the product side in equation 2. So all that I have left is the C2H4 added to hydrogen to make the C2H6. Those were the only things that didn't cancel out. And that's exactly what I want because that's my target equation. And it should always cancel out nicely. It should. If it's not, it means something went wrong. Like at the end, you should get your target equation. And we knew we were looking for ethene reacting with hydrogen to make ethane. If it's not working, it means I probably wrote down something wrong, like I maybe just missed something. So it should cancel out perfectly. All right. Then if, so the enthalpy of the reaction is like the energy of the reaction. So if it's negative, it's exothermic, it's releasing heat energy. Oops, okay. If it's positive delta H, that means it's endothermic, it's absorbing energy. But basically, when this first reaction occurs, okay, the ethene plus oxygen, this is a combustion reaction. Combustion reactions always generate heat. So as I have your ethene reacting with oxygen to make CO2 and water, right? That looks familiar. Combustion produces a lot of energy. Yeah, it is like a puzzle. I like these too. Okay, let's just read the chat. So combustion reaction always produces energy. So that negative 1410.9, it's the unit is in kilojoules. So we know that every time we take 1 mole of ethene, do a combustion reaction in the presence of oxygen, producing CO2 and H2O. Based on what bonds are broken and new bonds are formed, it releases 1,410.9 kilojoules of energy. So your enthalpy is the energy of the reaction. So if I'm trying to get the delta H from my target equation, which was the whole point of this to begin with, like we said, Hess's law, it's kind of intuitive. If you flip the equation, you change the sign of delta H. If you multiply through by a number, then you do the same thing to delta H. If you add the equations together, you add the delta H's. So kind of easy to remember. So we're going to take the negative 14.9. We're going to add to that the 1559.7. And then we're going to add the negative 285.8 to that. All right. And again, the negative sign, just make sure you don't keep track of it. So we've got the 1410.9 negative added to the 1559.7. And then basically we're subtracting the 285.8. And what we get here is a negative 137.0 kilojoules. So we know that for this particular equation of ethene plus hydrogen to make ethane, our delta H for this reaction is negative 137.0 kilojoules. And that's what the purpose of Hess's law is to do, is to figure out the enthalpy of the reaction. What's strange, obviously, is that you're getting it from other equations, but it kind of goes back to something we talked about on the very beginning, which is there is this energy stored right in the compound, in the structure. There's potential energy, and we can tap into it. And what we know is hydrocarbons are great at producing energy if we do the combustion reaction. So we do have to heat it, right? We got to get past that activation energy. But once we convert the ethene and oxygen to CO2 and H2O, that energy released by forming those new bonds of CO2 and H2O releases a lot of energy. And that's why we get a lot of energy out overall from the reaction. Okay, so this would be an exothermic reaction because it's negative. All right, releasing energy. So Hess's law is one way of getting a thermochemical reaction, meaning getting the enthalpy of the reaction. Using what are called the enthalpies of formation is also another way. So enthalpy of formation, right? This is the heat, delta H, for a substance. So any substance, water, CO2, ethene, they're all in a table. You can go and look them up. So if it is an element in its standard state, right? So standard conditions, like oxygen would be O2 gas. Zinc would be Zn solid. So Hess's law is going to be similar to the quiz questions. Like I can't, yeah. So let me double check that, Sophie, and let me make absolutely sure. So I'll have it ready for you on Tuesday for the review, just to make absolutely sure I'm telling you the right thing. All right. So I will check that. And we'll have that on the review. So the enthalpy of formation, these are all tabulated. And you'll notice the little dot symbol, that just means we're at standard conditions. If it's an element in the standard state, solid, liquid, gas, so like zinc would be a solid, oxygen would be a gas. Element, then enthalpy of formation is 0, because that's like its natural state. If I start making a compound like ozone or CO2 or water, then we can look those up and we can find the enthalpies of the formation. So standard state, room temperature, 25 degrees Celsius. Don't worry about that. Because I always thought it was interesting how, an intro standard is 273. And then when you get to Chem 2 and you start doing other things, it's 298. But anyway, don't worry about that. If it's a solution, 1 molar solution, this we don't worry about. You're never going to need to know that until Chem 2. So what we look at, there's this formula here, and it might look complicated, but there's a way to make it really easy. I think it's logical. So we're going to take ethene and combine it with water, and we're going to make ethanol. Okay. So this is a balanced equation. And what I'm looking at underneath, this is what I would go find in the table if I had to. The only thing you've got to be really careful about when you go to do these questions is you have to make sure you look at the state. Because what you'll notice is when you look at water, there's an enthalpy of formation for water in the solid state, in the gas state, and in the liquid state. So make sure you're grabbing the right one. It's easy to grab the wrong one. All right, so the heat of formation, I'm just going to put a little note next to this. I think it froze. The heat of formation, what you want to make sure and look at is you want to check the state. Make sure that you have the right state when you look at the table. Okay, because for the homework, you're going to just go and check the table. All right, so what this is saying is the heat of formation, right? As ethanol is formed, right, it has this energy, this potential energy, this energy of the compound, and it has a negative 277.7 kilojoule per mole. Water, negative 285.8, and then the ethene, positive 52.26. So what is being formed? I know that sounds simple, but that's our product, right? So we know that the ethanol is what is being formed. But the ethene and the water, right, these are being consumed. So basically, if you look at the formula, you're going to take products, right? What's being formed and subtract the reactants because that's what's being consumed. These are heats of formation, right? So as this is formed, this is the heat, right? But the water, that's not being formed, it's being consumed. So basically you're changing the sign and you do that by subtraction, right? Because we're not forming water in this equation, we're consuming it. So instead of negative 285, it would be a positive 285. So basically all you need to remember is you take products and you minus the reactants. We'll worry about the rest of that, like the sum and the n. We're going to worry about that in the next example. All right, so we'll come back to the n and the all that. So what I'm going to do to find the delta H of this reaction is I'm going to take my products, right, what's being formed, the ethanol, the negative 277.7, and then I'm going to subtract what I have on the reactant side, which is the 52.26 minus the 285.8. All right, now you can do this step by step, but here's what made sense to me because I don't know, I like to make it as simple as I can, and this seemed simpler to me. If it's on the product side, it's being formed, so the heat of formation value stays the same, right? Negative 277.7. If I distribute the negative through the parentheses, whatever's on the reactant side isn't being formed, it's being reacted, right? So it's going to change the sign. So instead of a positive 52.26, it becomes a negative 52.26. And instead of a negative 285.8 for water, it becomes a positive 285.8 for water. But you see what I did is all I did is I distributed that negative inside the parentheses, right? So positive 52.26 became negative, and then the negative, right, when you minus the negative of 285.8 for water, right, instead of the negative here, it becomes a positive. So when I was doing these quickly, right, anything on the product side, just leave it. Anything on the reactant side, change the sign and add it together, right? Or you can do it this way, just take products minus reactants, but it's the same thing. So I'm going to take the 277.7 negative, add to that 52.26, and then, sorry, hold on, go back. 277.7 negative minus the 52.26, and then add to that the 285.8. This one, not overly concerned with decimal places, but we would follow decimal places. So negative 44.2 kilojoules. All right, so that would be the delta H for this reaction, looking at the heats of formation. Now, you can get the delta H for the reaction through Hess's law. Oops, that's the wrong page. So if we went and did the same problems we were doing, that's why I put it over here. If we were going to find the heat of reaction using Hess's law, and we had some target equations given to us, we could do that methodology too. This is another way of getting the heat of the reaction. So this is another way of doing a thermochemical equation. So now we have this chemical equation, and we know that if we take ethene, react it with water to make ethanol, the delta H of that reaction is negative 44.2 kilojoules. All right, so another exothermic process. All right, so let's try another one where now it's going to come into play that we have to talk about N. All right, N just means moles. And what you'll notice is the heat of formation is per mole. So for 1 mole of ethanol, 277.7. But what if there had been 2, right? So we've got octane reacting with oxygen, another combustion reaction making CO2 and H2O. So looking at my heats of formation, what I would do, just so I don't lose track, is for the water, it has a coefficient of 18. All right, so I'm going to multiply that by 18. For the CO2, coefficient of 16. Oxygen is a 0, so it doesn't matter what the coefficient is. And that's like what we talked about. Any element in its standard state will have 0 for the heat of formation. And then for the octane, we've got 2 of those. So I just want to make sure and multiply that by 2, the 249.95. All right, so if you want to do it where you have products minus reactants, because that's what the formula says, let's do it that way. All right, so products, I'm going to use big brackets I've got 16 times negative 393.5. And I would add that to 18 times negative 241.8. Okay, so this is all my products. And then I would minus on the reactant side, I have 2 times negative 249.95. All right, so these are my reactants. Okay, so as I mentioned, when you subtract the negative, it's going to become a positive. So any reactant, basically, if you want to just think, I'm just going to add them all together. If you do that, just change the sign of the reactants or keep it this way, products minus reactants. Okay, so first thing I'm going to do is take that 393.5, multiply it by 16. Okay, so this right here, I get negative 6,296. And then if I take the 241.8, multiply that by 18, I get negative stays, right? 4,352.4. And then if I minus, we've got the 249.95 times 2. That would be negative 499.9. Okay, so all I did at this step was just multiplied, right? Multiplied the coefficients. So back up here in the formula, when it says the heat of formation times N, right? N is that coefficient from the balanced equation. So your heat of formation is always given in per mole, right? So for 1 mole of water, notice again, like I mentioned, water up here in the previous example was 285.8, and here it's 241.8, and it's because the state changed, right? So instead of liquid water, in this equation, we've got gas. So that's why that formula is slightly, or sorry, the heat of formation is slightly different. So that's what I was mentioning over here. Make sure you check the state when you go to look at the table, because water liquid and water gas has 2 different values. All right. So we've got the 16 times negative 393.5 is where I got the negative 6,296. 18 times the negative 241.8 is where I got the negative 4,352.4. And then 2 times the 249.95 is where I got the 499.9. All right, so in the parentheses, the first parentheses, I'm going to take the 6296 and the 4352.4, both negative, add those together. So this becomes negative 10,648.4. That's a comma, sorry, minus negative 499.9. Okay, so I'm going to take negative 10,648.4, minusing the negative means I'm now adding it. All right. So when I add all that together, I get a delta H for the reaction of negative 10,148.5 kilojoules. All right, which is a lot of energy, right? So that's why octane is pretty good source of energy for our combustion engine. All right. So this is again another way to get the heat of the reaction. The negative delta H, just reviewing some thermochem, right? That tells us that this is an exothermic reaction. But one way you can get the delta H is using Hess's law, or this is another way, which is by using the heats of formation. So if you use the heat of formation, just make sure you don't forget the coefficients in front. And when you go to use the table, just make absolutely sure you've grabbed the right state, because you'll see water has a value for gas, for liquid, for solid. So make sure you've got the right one. All right. Okay, so that's chapter 7. And as I mentioned, I think what I'd like to do, just for the sake of the videos, is that I don't have to break up chapter 8 videos or post, because if we keep going, chapter 7 and 8 are going to be in the same video. So what I'm going to do is actually go ahead and take a break now. I know it's a little bit early. It's 11:45. Let's come back at 12. So instead of meeting at 12:30, let's meet into the second room at 12. So everybody take a 15-minute break, meet you in the part 2, but I think this will work better for posting the video. So I'll see you back in the part 2 room in 15 minutes.